For many years, the Big Bang Theory has been the leading explanation for the universe's origin. It's the most widely accepted idea among scientists. It's like the foundation of a giant puzzle, giving us a framework to understand the vastness of space. But like any good mystery, there's always more to uncover. Scientists are always asking questions, looking for new clues to help us understand the universe even better. Could there be another explanation? A different way to understand how everything began? Imagine a point so small, so incredibly hot and dense, that it's almost impossible to comprehend. That's the Big Bang in a nutshell. This tiny dot exploded with unimaginable force, creating space and time as we know it. This explosion wasn't a one-time event. The universe has been expanding ever since, like a balloon inflating bigger and bigger. Galaxies are moving apart and the space between them is stretching, just like the Big Bang Theory predicts. Here's where things get a bit trickier. The Big Bang Theory relies on two mysterious ingredients: dark matter and dark energy. These invisible forces are thought to make up a whopping 95% of the universe. Dark matter acts like an invisible glue, holding galaxies together. Dark energy, on the other hand, is like a cosmic accelerator, pushing everything apart at an ever-increasing speed. The problem? We've never actually dark matter or dark energy directly. Enter Professor Richard Liu, a scientist with a bold new idea. He challenges the Big Bang Theory with a concept called temporal singularities. Instead of one massive explosion, Liu proposes a universe born from multiple bursts over time. These bursts, he suggests, are like cosmic fireworks going off at different points in space and time. Each burst creates a surge of energy and matter, ultimately forming the stars, planets, and galaxies we see today. Liu's theory offers an intriguing alternative to the Big Bang. Instead of everything happening at once, the universe could have been built in stages. Each burst would add to the existing structure, gradually shaping the cosmos into what we observe today. This idea might also explain the accelerating expansion of the universe without relying on dark energy. The bursts themselves could provide the outward push, eliminating the need for an invisible force. The search for evidence is one of the most exciting and challenging aspects of modern science. When a new theory emerges, especially one as bold and intriguing as Liu's, it sparks a wave of curiosity and debate across the scientific community. But how do we actually go about proving such a theory? What does it take to move from speculation to solid, undeniable evidence? Liu's theory is definitely captivating, offering a fresh perspective on the origins and structure of our universe. It challenges some of our most fundamental assumptions and invites us to look at the cosmos in a completely new way. However, it's important to remember that at this stage, it's still just that, a theory. In science, a theory is more than just a guess, but it still needs to be rigorously tested and supported by evidence before it can be accepted as fact. So far, we haven't directly observed these temporal singularities that Liu describes. They remain hypothetical, existing only in mathematical models and theoretical discussions. The universe is vast and mysterious, and there are still many regions and phenomena that remain hidden from our view. Our current telescopes, as advanced as they are, simply aren't powerful enough to peer all the way back to the very beginning of time. Even with cutting-edge instruments like the James Webb and Hubble space telescopes, there are limits to how far we can see. The earliest moments of the universe are shrouded in darkness, beyond the reach of our most sensitive detectors. Despite these challenges, scientists around the world are actively searching for evidence that could support or refute Liu's idea. This process involves not just looking deeper into space, but also re-examining existing data, developing new models, and collaborating across disciplines. The search for answers is a global effort, uniting astronomers, physicists, and mathematicians in a shared quest for understanding. One of the most promising places to look for clues is in the cosmic microwave background radiation, the faint afterglow left over from the Big Bang. This ancient light carries with it a wealth of information about the early universe, and scientists are constantly analyzing it for subtle patterns or anomalies that could hint at new physics. Finding these clues is absolutely crucial. If researchers can identify specific signatures in the cosmic microwave background or other astronomical data that match the predictions of Liu's theory, it would be a groundbreaking discovery. Until then, the search continues. driven by curiosity, skepticism, and the hope of uncovering the universe's deepest secrets. When we look up at the night sky and ponder the origins of everything we see, two major theories stand out, each offering a different story about how our universe began and how it has evolved over billions of years. But how do these two theories really compare? What evidence supports them, and where do they fall short? Let's take a closer look at the tale of two cosmic models that have shaped our understanding of the universe. The first and most widely accepted theory is the Big Bang. For nearly a century, the Big Bang has been the reigning champion in cosmology, providing a comprehensive framework for how the universe expanded from an incredibly hot, dense state into the vast cosmos we observe today. This theory is not just a wild guess. It's supported by a wealth of observational evidence gathered by generations of astronomers and physicists. One of the most compelling pieces of evidence for the Big Bang is the observation that galaxies are moving away from each other. This discovery, first made by Edwin Hubble in the 1920s, revealed that the universe is expanding, and it's been a cornerstone of modern cosmology ever since. When we look at distant galaxies, we see that their light is stretched or redshifted, indicating they are racing away from us and from each other at incredible speeds. Another crucial clue comes from the cosmic microwave background radiation, a faint afterglow left over from the early universe. This radiation, first detected in the 1960s, is like a snapshot of the universe when it was just 380,000 years old. Its uniformity and tiny fluctuations have been mapped in exquisite detail by satellites, providing strong support for the Big Bang model. We also see evidence in the very makeup of the universe itself. The abundance of light elements, like hydrogen, helium, and traces of lithium, matches the predictions made by the Big Bang theory. These elements were forged in the first few minutes after the universe began, and their proportions are a cosmic fingerprint that matches what we observe today. However, the Big Bang model isn't without its mysteries. To fully explain the way galaxies move and the universe expands, scientists have had to introduce two mysterious components: dark matter and dark energy. These invisible forces make up about 95% of the universe, yet we haven't directly detected them. Their existence is inferred from their gravitational effects and the way the universe behaves on large scales, but their true nature remains one of the biggest puzzles in science. This is where alternative theories like Liu's model come into play. Liu's theory offers a bold new approach by attempting to explain the universe's behavior without relying on dark matter or dark energy. It challenges the status quo and invites us to rethink some of our most fundamental assumptions about the cosmos. But while Liu's theory is intriguing and could potentially solve some of the Big Bang's biggest mysteries, it currently lacks the same level of observational support. The data simply isn't there yet to elevate it to the status of the Big Bang. For now, the Big Bang remains the best explanation we have, but the search for answers continues, and the universe may still have surprises in store. The search for evidence continues. Across the globe, teams of dedicated astronomers and astrophysicists are working tirelessly, peering deep into the night sky, hoping to uncover the secrets woven into the very fabric of the cosmos. Their quest is not just a scientific endeavor, but a journey of curiosity and wonder, as they attempt to answer some of the most profound questions humanity has ever asked. How did the universe begin? What hidden forces shaped its evolution? And could there be clues hidden in plain sight that point to new physics beyond our current understanding? Scientists are looking for specific signatures in the universe that could support Liu's theory. This means sifting through mountains of data collected by powerful telescopes, both on the ground and in space, searching for patterns or anomalies that might reveal the presence of phenomena predicted by new theoretical models. Every pixel in a cosmic image, every data point in a spectrum, could hold the key to a groundbreaking discovery. One such signature is the presence of redshift jumps, which are sudden, unexpected changes in the observed wavelengths of light coming from distant galaxies. Normally, as galaxies move away from us, their light stretches and shifts toward the red end of the spectrum, a phenomenon known as redshift, which is a cornerstone of our understanding of the expanding universe. But if, in the midst of this smooth progression, scientists detect abrupt jumps or discontinuities, it could signal something extraordinary at play. These redshift jumps are essentially sudden changes in the color of light from distant galaxies. Such anomalies might be caused by dramatic events or structures in the universe, such as temporal singularities, regions where the normal flow of time is disrupted, possibly by exotic forms of energy or matter. Detecting these jumps requires not only precise instruments, but also innovative data analysis techniques and a willingness to question established assumptions. These jumps could indicate the presence of temporal singularities. If confirmed, this would be a revolutionary discovery, suggesting that the universe contains regions where the laws of physics as we know them break down, and time itself may behave in unexpected ways. Such findings would open up entirely new avenues of research, challenging our understanding of cosmology and the nature of reality itself. By analyzing the light from the most distant objects in the universe, scientists hope to peer back in time, to the very moments after the Big Bang. Each photon of light that reaches us from these remote galaxies has traveled billions of years, carrying with it a record of cosmic history. By carefully studying these ancient signals, researchers can reconstruct the events that shaped the early universe, and perhaps even glimpse the processes that set everything in motion. In doing so, we might actually be able to unravel the mysteries of the universe's birth. The answers could reshape our understanding of space, time, and the fundamental forces that govern everything we see. Each new discovery brings us a step closer to comprehending the grand cosmic tapestry, revealing how the smallest details can have the most profound implications. New telescopes and advanced technologies are constantly pushing the boundaries of our understanding, allowing us to see deeper and with greater clarity than ever before. Instruments like the James Webb Space Telescope and next-generation observatories are opening up new windows into the universe, enabling scientists to detect faint signals and subtle patterns that were previously beyond our reach. With every breakthrough, we are brought closer to answers. The excitement of discovery fuels the passion of scientists everywhere, as they celebrate each new insight and prepare for the next challenge. The cosmic tapestry is vast and complex, but with perseverance, ingenuity, and ever-improving technology, humanity continues its quest to unravel the deepest mysteries of the universe. The beauty of science lies in its constant evolution. New ideas challenge old assumptions, leading to new discoveries and a deeper understanding of our place in the cosmos. Whether it's the Big Bang or temporal singularities, the pursuit of knowledge really drives us forward. As we continue to explore the universe and its origins, one thing remains certain. The story of our universe is an ever-unfolding adventure, full of wonder, mystery,